Welcome to Selected Homework Problems. Let's jump right into it with 256. So 256 says something. It says, verify each identity using differentiation. So these problems aren't that hard, but the wording's a little confusing, so I did this to clarify. So verify with differentiation, and then use the indicated U substitution to write the integral in the form of that integral of f of u. So we're trying to verify this antiderivative. So all we're going to do is take the derivative of the second thing and hope that it equals the integrand. So if we look at the derivative with respect to x of 2 out of 15, x plus 1 to the 3 halves, times 3x minus 2 plus c, it's not an easy derivative. It's not super hard, but it's a little messy. We're hoping that it equals that integrand. So if we do that, we're going to need the product rule. All right, so let's this be f, and that be g. The derivative of the first, 2/15 times 3 halves. Inside stays the same. Subtract an exponent, multiply by the derivative of the inside. That's just f prime. And all of that times g. So again, that's just f prime with the chain rule. And that's just g. Plus f, which is 2/15, x plus 1 to the 3 halves, times g prime, which is 3. That's the product rule. Derivative of that plus c is 0. So now we just simplify and hope it doesn't, right? We're hoping that it equals this. It doesn't look like it, but let's simplify and see what happens. So we get some cancellation here. We just get a 5 in the denominator on that one. Second one, we have a little cancellation. We just get a 5 in the denominator. Okay, good sign. So this first one becomes 1/5 times x plus 1 to the 1/2 times 3x minus 2. And the second one just becomes 2/5 times x plus 1 to the 3 halves. Now you might be saying, it's not the same. We lose is the first problem. It's not even true. The book is lying to us. Well, let's simplify. All right. So let's factor out what they have in common. We factor out a 1/5 times x plus 1 to the 1/2. What are we left with? Well, this whole thing is gone. We factored it all out. We're just left with a 3x minus 2. And then we factored out 1 of the fifths. There's still a 2. And we factored out an x plus 1 to the 1/2, but there's still an x plus 1 to the 2 halves left over. And now look what happens. We simplify that inside. We get 3x plus 2x is 5x. And then minus 2 plus 2 cancels each other out. The 5 cancels like so. And we're just left with x times the square root of x plus 1. Is that what we wanted? Oh, that's what we wanted. We've checked our answer. It's not a super easy problem to start off with, but it is at least not a false problem. All right, so we checked it. Great. Wait, we can actually, this guy can be kind of like 3 check marks. It's like a sideways check mark. You can make this like a curvy check mark. No, it doesn't work. All right, triple check mark guy. And that's half of the problem. And then it says use the U substitution to make it work, to set it up. So we're looking at the integral from times x times square root of x plus 1 dx. And it wants us to use u is x plus 1. So du dx is just 1, which means du is the same thing as dx. This becomes the integral of x can't do anything with that right now, times the square root of u times du like so. And then again, if we want to get rid of x, so let's use this. If u is x plus 1, then u minus 1 is x. Just subtract 1 from both sides. And if we subtract 1 from both sides, we're going to get u minus 1 times the square root of u du, which is all that the problem wants us to do. If we were actually evaluating this all out, we'd distribute this and simplify. But technically, this is done for what the problem is asking us to do. It wanted us to write it as an integral just with terms of u. And that's what we want for this problem. All right, next one is 271. Use a suitable change of variable to determine the indefinite integral. Integral x times 1 minus x to the 99th power dx. Now you have two choices to solve this problem. First choice, you could write this as 1 minus x times 1 minus x times 1 minus x times 1 minus x 99 times, and do a little bit of algebra, multiply it out. Please never do that, but it is an option. Or you could use a u substitution. Let's have this be our inside. Have this be our inside, our u. The u is just going to be 1 minus x. So the derivative is just negative 1. So du is the opposite of dx. And again, we have the same thing as in the last problem where, all right, we can't get rid of this immediately, but we'll be able to take care of it. All right, so it's weird that in the book's problems, they don't really show this method until like almost the end, but it pops up at like the early homework problems. I don't like that. But book's not perfect. It's a work in progress. All right, so what we have here when we do the substitution, read the integral x. Let's leave that alone for now. The next part becomes u to the 99th power. Dx becomes, well, if du is the opposite of dx, that means dx is the opposite of du. It becomes negative du like so, and the negative can be factored out in front. And just like before, well, if u is 1 minus x, solve for x. Subtract 1, multiply both sides by a negative 1. You're going to get x as 1 minus u. And be very careful. That doesn't mean that u and x are the same thing. It just means they're related in kind of a weird way. So x is 1 minus u, so we get 1 minus u times u to the 99th power with that negative out in front and du. We're almost ready to integrate. Again, it looks very similar to what we started with, but now we don't have to FOIL 99 times. We can just distribute to get the opposite of u to the 99th minus u to the 100th, which is much more achievable. So power rule. And then you can have a negative on the outside, or you can distribute it depending on whether you want parentheses. Use the power rule again. And then translate everything into x's for our final answer. Again, factoring it here is best. I'll accept this as a final answer though. U is 1 minus x. Oh, I don't have room. All right, well, if I don't have room, it's less of a good answer. But yeah, this is a perfectly acceptable final answer here. But the best final answer would be to clean things up by factoring. We factor out 100, 1 minus x's. What are we left over? Well, if we factor out 100 of those guys, we're left with a negative 1 over 100. We factor out 100 here, we're left with the 1 over 100, and then 1 left. that we can simplify. First term is just chilling. Second term, we can clean that up by distributing to get 1 over 101 minus 1 over 101x. It doesn't simplify as nicely as I wanted it to. Because even though these are really similar, sometimes denominators being similar makes it the worst. So to find a common denominator, to add these together, we have to multiply this one by 101 over 101 and multiply this one by 100 over 100. So it's not that nice, honestly, but it's still simpler than what we had on the last page. So we're going to get 100 minus 101 is going to be negative 1. And 100 times 101 is like so. Which is, again, another good final answer. Or you could factor a negative 1 over 101 from everything. Again, I realize I said that I would accept an answer 20 steps ago. But if you just really want to be a superstar, you can do it. And in fact, if you really want to be a superstar, even better, oh man, even better would be to actually factor out even more of a fraction, the 10/100. Like so. Because then we just get 1 plus 100x, which looks a little nicer, I think. And there's a lot of opportunities for simple errors here, but I'm pretty sure that these are the same. Here's one way of not proving that they're the same, but visualizing and checking your work. Let's graph these functions. My final answer was negative 1 over 10,100 times 1 minus x to the 100th power. Yep. Times 1 plus 100x. This is my answer. Nice function, right? Here, let's wait. Can we get some axis? We're really going off the rails now. Can I set this up so that it's like useful? Can we really visualize this? Well, you can see it a little bit better now, right? Okay. Look, we can finally see what's happening now. All right, maybe that was one too many. Look, beautiful. All right, so if we have x going from negative 0.1 to 2.1, y going from negative 0.0005 and 0.0005, because what's happening is we have such high exponents. And remember, like in general, as you go from x cubed to x to the 4th to x to the 6th, it kind of looks the same. It just gets flatter and then steeper. It's like really flat in the middle because an exponent of a fraction makes it gets really close to 0. And then there's like this tipping point. There's another factor, and then it shoots off to infinity. And it shoots off very, very quickly. So the question is this the same function as our first answer that we had over here? Negative 1 over 100, 1 minus x to the 100th, plus 1 over 101 times 1 minus x to the 101. Thank goodness, I was worried. So you can, again, this is not a proof, but graphically you can see that they look like they're the same function. All right. Oh, man. And again, as one more note, I would accept this as a final answer. But this is a really good final answer. It's so much cleaner. Okay. Let's move on, Jason. The 287. All right, 287. It's just a complicated indefinite integral. Sine squared minus 2 sine times sine cubed minus 3 sine squared cubed times cosine. It just keeps on going. So this is very easy to get overwhelmed, and that's why I chose it. It's a really long, looks terrible problem. I don't think it's actually going to be that bad, but let's look. So there's a lot going on. We have a couple options. We can try to find a u and just make a guess and see if it works out. We can investigate a little bit. We can try to use some trig formulas to simplify a little bit. Maybe Pythagorean identity, because we got a bunch of sine squareds going around. And it's not obvious what to do. So those are your strategies. You're not going to know right off the bat. I don't know right off the bat. I have a suspicion, but I don't know. And these are your options. So one of the things to think about, one of the things that jumps out to me at the very start of this is we have a cosine of theta right in front of the d theta. We have a cosine of theta being multiplied by all of this. So I'm guessing that our u substitution should have something to do with sine. And then hopefully this is going to be part of that du that goes away. So I think if we do a u substitution, it looks promising to have something to do with sine. There's a lot of choices for an inside function. You could do sine squared. Now the derivative would be 2 sine of theta times cosine of theta, but we don't have a sine that's just attached. We could maybe distribute. Oh, we can't distribute because of the 3 up here. Otherwise, I would think maybe put this together might make it easier. Well, this is being cubed. What would it look like if we had this be our u? What's the derivative of this inside? The derivative of this inside is 3 sine squared times cosine minus 6 sine times cosine, which is actually really close to this other stuff. I can't do it in my head, but it actually looks really close to what happens if you multiplied the cosine by this other thing. So let's try it. Let's try it and run with that. That's kind of our best start. And if it doesn't work, it'll be a good opportunity to show what happens when it doesn't work and how we can try something else. That's kind of my personal thought process for how to approach this problem at the beginning. Look at a couple ways, think about your options, choose one, and if it doesn't work, go back, choose another. So let's say that u is going to be sine cubed of theta minus 3 sine squared of theta. And again, the reason why I'm not rewriting any of this is because this was a guess and the guess looked promising. I don't know whether it will work, but it looked promising. So in that case, the derivative is going to be 3 sine squared of theta minus, chain rule, times the cosine of theta minus 6 sine of theta, cosine of theta. We can multiply and get the d theta over there using what we know about the substitution rule. And let's also factor out a 3 and a cosine. I'm doing this because I know there's a cosine factored out before, and I want it to become this. If we factor out a 3 and a cosine, I'm curious what we're going to get. Again, there's going to be a d theta at the end. Factor out a 3 and a cosine, we're left with sine squared of theta. That makes me happy. Minus 2 sine of theta. Ooh, that makes me happy too. Because look how similar these two blue underlined things are. All we need is a 3. So again, there's that 2 methods that we can use if we're only off by a constant. We can solve for d theta, and that's fine. Or we can just sneak a 3 in there. This is all being multiplied. So if we multiply a 3 by everything and divide everything by 1/3, well, multiplying constant multiples can come out or go inside of integrals as we want. And now we actually have a super nice u sub. So this is going to be 1/3 times the integral. Everything underlined in blue is exactly equal to du. Everything underlined in blue goes away. It's just du. And then up here in the red underline, that's just u cubed. Oh, it looks so bad. And now it looks so good. What is this, like a Hollywood movie where the girl takes off her glasses? There are actually some things I could say after that I won't. Let's take the antiderivative. Add a power, divide by the power, plus c. So we get 1/12. U, what is u? Raised to the 4th power plus c. Well, u is sine cubed of theta minus 3 sine squared of theta. And that's it. You could check your answer with a derivative. I'm not going to here. You could check your answer with technology. That could work too, but there we go. Nice. That was 287. 307. I think these last two ones are the more weirder ones that I wanted to show you. Use a change of variables to show the definite integral is equal to 0. All right, so it wants us to change the variables and show this is equal to 0, which is a little weird, and that's like, it sounds confusing what it wants us to do. But all it wants us to do is evaluate this integral. That's all it's asking. It says just evaluate the integral and then show me that it's 0. It's just trying to give you a hint and say evaluate the integral with this hint. But it's worded kind of weirdly. So if we do that, what we get? Well, what are we going to let u be? Now, I'm hoping your gut says let u be t squared. And that's really nice because we have a t on the outside. And that works. In fact, let's do that. I want to show what happens if you do that. There's a better choice here. But as I've been training and teaching, I hope that this is what you see, even though there's a better choice. This will still work. And that's an important thing for integrals. You don't always have to find the best choice, especially in complicated problems. Sometimes it's best to just start and go from there. And with more practice, you'll get better at seeing things. If u is t squared, the derivative of u with respect to t is 2t. So du is 2t dt. So if we just multiplied everything by 2 and divide everything by 1/2, then everything that's underlined just becomes du. We get 1/2. The integral, if we're using a u substitution for a definite integral, have to update those limits. So if t is 0, then what is u? Well, u is t squared. Well, 0 squared is 0. We update this to a 0. And if t is the square root of pi, what does u become? U becomes pi. Great. Now the blue stuff just becomes du. And we're left with cosine of t squared, which is u, times sine of t squared, which is u. We still can't integrate this. Because we have two functions multiplied by each other, that's hard. So we can do another substitution. Because the derivative of sine is cosine. So if we have this be our new variable, then we have its derivative and we can do another u substitution. So that's why I said this isn't the best choice. But by doing that substitution, we still get an easier problem. So even though there was a way to do this all in one substitution, it's pretty messy, hard to see. So that's fine. Just do what you see. And now we have a simpler problem. We're going to do another substitution, but we're doing it in 2 small steps instead of 1 big step, which is usually a lot more manageable. So do not use u anymore. U already means something. You can use x. You can use not t. W is the very common choice here, but you have a lot of options. So let's say, well, I know the derivative of sine is cosine. So if this is my w, well, then we're good to go. So let's let w be the sine of u. Oh, yeah. I'm glad we got one of these popping up. So then what is the derivative of w with respect to u? Don't worry about it. It's going to be cosine of u. So dw is just cosine of u du, which is fantastic because that's the yellow underlined stuff. We get 1/2 integral. Oh, we updated our variable again. Let's update our limits of integration again. Well, if u is 0, then what is w? W is a cosine of 0. Cosine of 0 is 1. And then if u is I'm running out of room. I'm writing it here. If u is pi, well, what does w become? The cosine of pi. Wait a minute. I made a goof. W is the sine. It's not the cosine. If u is 0, w is the sine of 0. Sine of 0 is 0. And if u is pi, w is sine of pi, which is, sine of pi is the y-coordinate on the unit circle at pi radians. The y-coordinate right here is also 0. So we get the integral from 0 to 0. Everything in the yellow just becomes dw. And the green just becomes w. We're done. We're done. We don't have to integrate this at all. Why? We're taking the integral from 0 to 0. I'm saying, look at this function. Look at this function. What's the area under this function between 0 and 0? There's no area. That's a line. Lines don't have area. It's 0. All right? So, I mean, you could evaluate it. You don't have to. We know it's 0 from properties of integration. All right? Fun fact. The whole state of Wyoming has the same area code. It's 307. So on like March 7th, you know, that's a special day. Okay. 315. Last problem for this video. It's also a wacky one. I haven't really looked at it. Let's see. 315. Find the area under the graph of g of t equals t over 1 minus t squared to the 8th power. Let me make sure I copied it down right. T over 1 minus t squared to the 8th power. Okay, we want the area under the curve. Area, I need to scroll down. I'm gonna start looking at 314 if I don't scroll down. So area under the curve on the interval from 0 to x. Area under curve on the interval 0 to x. And it's telling us that x is... So we're looking at the interval from 0 to x. We also know x is on the interval from 0 to 1. Exclusive. And a over 0 is... a is positive, and it's a fixed constant. So we're getting so much information here, which can be overwhelming. Evaluate the limit as x goes to 1. The limit of this area as x goes to 1. So there's so much happening here. It's so easy to get overwhelmed here. Break it down into little pieces. Break down the pieces of the information. Okay, we got a function. We're going to need the area under the curve, so there's going to be an integral. We're looking at this region. Okay, what is x? X is a variable, and it's going to be between 0 and 1, all right? What is A? A is a positive constant, which is good, because if A is negative, then this function looks radically different. Find the area, the limit of this area as X goes to 1. And let's say you're still unsure about this. You don't like A's. Well, you can do this without knowing anything about it, but it's a little harder. Let's visualize this. Let's visualize this function. So g of t is equal to t divided by 1 minus t squared raised to the 8th power. I don't know what limits of like the viewing window will make sense, but let's. Okay, so if a is 1, this is t over 1 minus t squared. We know a is going to be something positive. Well, let's play around here. Let me use a shortcut to show. I want to make sure I can show you the whole screen, because it's cropping a little bit right now, which is intentional because of I want to crop out the toolbar in my Blackboard application. And I want to show you something fun that you can do this. How does this, so you can slide this around to see, you know, what happens for different A's. But you can actually get it even a little bit more in depth on this one. If you set the limits for A's, let's say, so we know A is positive. It's some positive number. Let's start with that. So let's look at what this function looks like for different A's. So as A is getting bigger, look what's happening. All right, that's kind of weird. Let's slow it down. Slow it down. Look. So this middle part has basically the same shape for any A. And as A is getting bigger, the middle part is getting more and more vertically stretched. It's getting steeper and steeper. And then at specific values of A, you might have a whoop and you might have a whoop. Okay? But here's the good news. Remember, it told us that we're only looking at the interval from 0 to x. Now we're looking at x going to 1. So let's forget about all that other stuff. And remember that we're only looking at the area under this curve from 0 to 1. Oh, we'll have to zoom out a little bit. And now let's see that's actually changing. We're looking at the area under this curve as x is approaching 1. Again, at 1, this is not defined anymore. But you can still have an integral. That'll be called an improper integral. We talk about that much later. So as a is changing, this function is slightly changing, but this is in general what's happening. All right. Now let's go back and get the problem done. So the area under the curve on that interval, we know that. The area under the curve on the interval is going to be the integral from 0 to x of this function dt. All right, and we can evaluate this integral and do stuff as long as t is not equal to 1. T is equal to 1, then we have a problem. But we know that we're only going up to x, and we know x is never hitting 1. So no problem here. We need to evaluate this integral. We're going to use a u substitution. What if this is our inside function? The derivative of this inside is negative 2t, which is nice, because we can get a negative 2t. So we'll say let u be 1 minus t squared. Well then du dt is negative 2t, which means du is negative 2t dt, which we can get by multiplying this function by negative 2 and dividing this function by negative 2. Now, everything underlined in blue becomes just a du. This becomes the integral from it becomes negative 1/2 times the integral update those limits. If t is equal to 0, what is u? T equals 0, u is 1. If t is equal to x, well, what is u? It's going to be 1 minus x squared. We're now going from 1 to 1 minus x squared. Pause. You don't literally pause the video. If you pause the video, I'm never going to start speaking again. They may have paused the video before hearing that, in which case they're just sitting in front of a paused video waiting for me forever. Anyway, remember that x is between 0 and 1. So in this, the bottom limit of integration is actually bigger than the top. That's okay, right? We can take the integral from 1 to 0 and stuff like that. That's no problem. And in fact, we have a property that says that you can switch those if you add a negative, which we already have. If it makes you uncomfortable, you can switch it, but you don't have to. A definite integral will work out completely the same regardless. Also, a while back when we introduced that property, very short tangent. Remember when we introduced this property and I said, all right, if we have the integral from a to b of some function, that's the negative integral from b to a of that function with respect to x. And I said, we don't really see why this is true right now, but we will later. One of the ways of seeing why this is true is the fundamental theorem of calculus. The thing on the left is f of b minus f of a. And the thing on the right is the opposite of f of a minus f of b. Also, I should be really good. That's not how you do proofs. The way to do proofs is to start with one side and say, hey, look, the right-hand side is equal to that by the fundamental theorem of calculus. Distribute that negative. It's that. And again, by the fundamental theorem of calculus, that's the left-hand side. So you can really see where this comes into play. Graphically, still a little harder to visualize, but this is why we define it to be this way. It works with the fundamental theorem really nicely. Okay, so here we are. Everything in blue became a du. And be very careful. We're not left over with a u to the a. We're left over with a 1 over u to the a, or a u to the minus a. So be very careful on that one. And now, power rule. Remember your power rule. It says the power rule only works as long as the exponent isn't -1. Oh, drat. I was going to tell us why we had nothing to worry about. But go back to your power rule. Right? Power rule says x raised to the n dx is add a power and divide by that power, but that doesn't work if n is -1. Because if n is -1, we have 1 over x. That integral is a natural log of absolute value of x. And I was going to say, well, we don't have to worry about that, but I think we do, because it only tells us that a is positive. It doesn't guarantee that a is not 1. If a is 1, we got a natural log on our hands. So we actually do have to split this up into 2 cases. I'm curious where this is going to go, actually. I don't think the book intended this, but let's be precise. So, case 1, if a is not equal to 1, and then we'll also do something. What happens if a is equal to +1? Well, the second one should be easier, because if it's +1, we know what it is exactly. Right? It's just 1 over u. Which, again, antiderivative of 1 over u is a natural log of the absolute value of u, evaluated between here. That's going to be the natural log of 1 minus x squared minus the natural log of 1. Natural log of 1 is 0. And we're going to get negative 1/2 natural log of the absolute value of 1 minus x squared. And the question was, it said, don't just find the area. It said, find the area and then say, what happens? Oh, dear. There's always one doozy of a problem in every one of these assignments, at least one. I try to find them for you. What's happening as x is going to 1? Well, as x is going to 1, as x is going to 1, this approaches the natural log of 0. The natural log of 0 is negative infinity. It's not defined, but it approaches negative infinity. So what's negative infinity times negative 1/2? So as n goes to infinity, this whole thing becomes positive infinity. All right, let's see what case 1 is. Maybe case 1 will be better. Nice little surprise. Curious what they think about this problem. Which problem is this again? $3.15. They have an answer. I'm curious what their answer is. Anyway, yeah, they just say A is positive. Okay. Well, let's see the other case. Maybe the other case will be better, guys. Negative 1/2. We can use the power rule because we know A is not 1. And if we use the power rule, we add an exponent. It was negative A. Now it's negative A plus 1. And we divide by that exponent, negative A plus 1. We're evaluating from 1 to 1 minus x squared. Maybe this will be better. Let's write this as negative 1/2 times 1 minus a. And then when we plug in 1 minus x squared, we're going to get, yeah, maybe this is better. 1 minus x squared raised to the 1 minus a power minus 1 to the 1 minus a power. Okay. We know a is positive. So 1 minus a is just going to be some number 1 or less. And 1 to any number is still 1. So the second one is just 1. That's great. You get negative 1 over 2 times 1 minus a. Again, you really can see why it matters that a was not 1. That's why we had this. Times just 1 minus x squared. 1 minus a. Where is this problem going? And now we're curious. Sorry, it's not n goes to infinity. I always write that. It's as x goes to 1. The question is x goes to 1. What kind of happens? I don't know. Let's see. Let's do it together. All right. So, really what we need to figure out, this is the only piece with x. If we can figure out what this thing is doing, then we can figure out what everything else is doing. So let's go off to the side real quick and say, okay, what's the behavior of 1 minus x squared to the 1 minus a become? And this is hard to see. So I'm actually going to rewrite this. Because yes, as x goes to 1, this becomes 0 to something. Actually, I think that's fine. Right? As x goes to 1, this becomes 0 to the 1 minus a power. But that's not always 0. We have to look at, because 0 to the 0 is something. It's an indeterminate form for limits. We'd have to use like L'Hopital's rule or something. But let's look at our exponent. What is our exponent here? We know a is positive and a is not 1 because we're still under the umbrella of case number 1. This is good content, by the way. This is interesting. Maybe not interesting. Maybe it's overwhelming, but this is the kind of math that really does happen the higher and higher you go. So I think it's a good exposure for you guys. I'm really glad I chose this problem, and you don't want to hear this, but I'm really glad this is on your homework assignment. Okay, so no interfering October. So what happens? So what does 1 minus a look like? So in this interval, we know 1 minus a, the biggest it can get is 1. It can't be 0. Oh, okay. So 1 minus a has to be less than 1, and it won't be equal to 0. So that's what our exponent looks like. So it could be a positive number between 0 and 1, in which case this is 0. Or it could be a negative number. If it's a if it's a negative number, that's bad. Right? What's 0 to the negative 1? That's 1 over 0. All right. I'm 100% sure that this book gave the wrong stipulation for A. They really wanted you to say A is between 0 and 1. I'm almost positive. Okay. This is fine. We can salvage this. So, this is something that happens in math too. You're going to hate it. And also, I know you're thinking about this. No, this is not going to be on a quiz or an exam, but it will pop up in future classes depending on how far you're going. So this is also something that happens. So case 2, we knew that this area is going to infinity. Case 1, well, it depends. What is A doing? So we had a case depending on. So really, we our choice of 2 cases was wrong. We should have split this into 3 cases, but that's fine. We can do sub cases instead. Okay, so in blue, case 1A. This will be the nice one, right? Because if A is between 0 and 1, then that's this situation, right? If A is between 0 and 1, then 1 minus A is between 0 and 1 as well. And you can find this by multiplying both sides by negative 1. And that flips the direction. And then adding 1 to both sides. And if that's the case, then this guy (1 minus x squared to the 1 minus a), as x goes to 1, just becomes 0 to the 1 minus a, which is some number between 0 and 1, which is going to be 0 in this case. So if that happens, then the area, again, all under case 1a, area, which is this guy, goes to negative 1 over 2 times 1 minus a times 0 minus 1. And that simplifies down to just 1 over 2 times 1 minus a. Great. So in one case, we had an answer. Underline it in green. In a subcase, in another answer. And let's look at case 1b. Right? If a is bigger than 1. Well, if a is bigger than 1, then 1 minus a is negative. So 1 minus x squared, the 1 minus a approaches as x goes to infinity, as x goes to 1. Zero to some negative exponent. Undefined. And you can get an idea of what this is going to become. As x is going to negative 1, the inside is positive and going to 0. The inside's going to 0 from the right. That's going to 0 from the right. And we have just this sort of situation, 1 over something, because that's a negative exponent. So if this is like going to 0 for the right, this is not exact, but just think about it this way. It's going off to positive infinity. Great. And of course, if this is going off to positive infinity, well, then multiplying that by a negative number, which is actually not negative, it's still a positive number, because this is positive. No, this is negative, and we got another negative. I know this is terrible. If you're still watching, kudos to you. Maybe some people have already thrown their computer into the wall or something. I'll make a note about this guy. Right, we know 1 minus a is negative here in this case. So this is positive infinity. This is going to positive infinity. Positive infinity minus 1, still positive infinity. And then this becomes a positive number. So again, it just becomes positive infinity. Okay. So in this case, it also, the whole thing, the area goes to positive infinity as x approaches 1. So really, there was only 2 cases, because one of the subcases had the same situation. So if a is between 0 and 1, then the area approaches 1 over 2, 1 minus a. I said maybe case 1 would be better. Case 1 was not better, guys. Case 2 was the better one. I lied to you. Well, I was optimistic. And if a is bigger than or equal to 1, then the area approaches infinity as x approaches 1. And that's our answer. What does the book write for this? Okay, all right, Mr. All right, wise guy here. The book's trying to not show me the answer. All right, I can outsmart you, book. It won't let me click on it. All right, what does the book say for 315? I'm almost positive I know what they're doing, but I just want to see it. It doesn't even comment about what happens if a is equal to 1. What? So this should be greater than or equal to 1. But then they're basically the same as what we have. Huh. Yeah, but all right. Yeah, they should. So they didn't make a typo. There's a small error in their answer that this should include they should include the natural log case where we did the cases. So there's a small problem with the answer, but no, they did want you to look at this. Okay, it's just a hard problem. Let's visualize it. Or we already visualized it. In fact, I shouldn't erase it. All right, this is what's happening. Well, I want you to also look. Let's look at the integral from 0. Can we add 2 sliders? I don't think it'll let us add 2 sliders. We can look at the integral from 0 to 1, maybe, of g of t dt. So yes, it is undefined. It's going off to positive infinity. But what happens if a is between 0 and 1? Ah, if a is between 0 and 1, look what this integral becomes. 1 divided by 2 times 1 minus a. Right, small rounding error maybe. But look, for all these values of a between 0 and 1, there are rounding errors in how it computes the integral, probably. But they're the same thing. And then when a gets at least 1, then it's undefined. And again, this formula is not undefined, but it doesn't equal the formula anymore. And you can kind of see it graphically a little bit. There's like a tipping point. If a is less than 1, this area under this curve is finite. And if a is bigger than 1, it looks very similar. And that's one of the mind-blowing things about math. It looks similar, but it goes from finite at A is 0.9. It goes from an area of about an area of 5. And then let's just change this curve a little bit. It's infinitely bigger than 5. That's crazy, right? You don't believe me. You might not believe me. It's true. It's actually true. We're just changing the shape a little bit, but all of a sudden, it's not quite steep enough anymore. That there's an infinite, like it's a small little bar, but there's actually infinitely much area underneath that curve, which is wacky. And in fact, even the distance, if A was 0.99999, it's finite. Right? If A is 0.9, it's finite. 0.99, it's finite. 0.999, still finite. Look what's happening to the area. It's finite as long as A is less than 1. But what's happening to the area? The area is getting bigger and bigger as A is getting close to 1. So I said there's like a tipping point. Oh yeah, 0.9, it's 5, and then 1.1, it's undefined. Well, it's not really a tipping point. It's more of a limit going to infinity. So X is approaching 1. A is doing its other thing. There's all this stuff that's happening. This video could have been a 30-minute video if I just didn't go on so many rants. But I mean, that's, you know, these are optional videos anyway. And it gives me an opportunity to talk about complicated, complex, interesting things that you could never do in a classroom. I could not spend 30 minutes talking about this in a classroom. There's just not time. I'm just stealing your time outside of the classroom. I'm just stealing your time. Maybe you'd be reading a book, playing a game, hanging out with your family. Bring your family to these. Calculus is fun for the whole family. Okay. We're done, right? There's nothing else I wanted to show you. I mean, that's not exactly true. There's one more thing. It won't be that long. Let's add, if I use X, it's going to get a little confused. Let's think of B as X. So we want to know my claim. Actually, no, I don't want to do this. Never mind. I was going to show what, like that limit as X is going to 1 for a specific value of A, and I don't think it's worth it. Okay, this is our answer. We had to sub it into cases. You have to watch out. Power rule only works except for when the integral is the natural log. So watch out for that one. You might have to split things up into cases. This is super common when you're in higher level mathematics, saying, I don't know what A is, and our answer is going to be different depending on what it is. Split it up, and then it turns out, okay, we had to split it up even more. And that's okay too. Just like with the U substitution in this video, we had to do it twice because we didn't choose the best answer. That's okay. You don't need to see everything at the start. Make your steps and always be careful and reevaluate and take extra steps as necessary. So there we go. Another hour-long selected homework problems video. Let me know if you have questions. Have a great rest of your day.